In a previous lecture, we have seen that power series expansions can be a very powerful tool when you want to study the properties of an analytic function in a neighborhood of some point where it's analytic. However, it could also be that you want to study an analytic function in a neighborhood of singularity, a point where it's not analytic. And in that case, power series won't do. For example, if you have this function, e to the power 1 over z, then this function is obviously analytic in the whole complex plane, except for the origin. And so if you want to study it in a neighborhood of the origin, then ordinary power series are not very convenient. However, in this case, there's an obvious substitute for that. Namely, you can expand this function in terms of 1 over z instead. So you get this formula then simply by using the ordinary power series for the function, for the exponential function, and then inserting this 1 over z. So this is a very simple example of what we call a Laurent series. In general, a Laurent series is a series which contains both positive and negative powers of z. And this is a thing that we want to discuss in this lecture then. If you want, you can try to expand a function in a neighborhood of a point where it's not analytic, but it's more general to do it in a region of this type. You consider two concentric circles like this, and you have a function which is analytic in this region then. And then you would like to find a kind of representation formula of this kind in this region without knowing anything really about what happens in here or outside here. The idea now is that we try to copy the method we had for power series expansion. But the problem is that if you just draw a circle around here, you cannot use the Cauchy integral formula directly because the function will not be analytic in the interior of this circle here now. So what you do is instead the following. You start drawing a circle like this, going around here. But when you're going to get up here, then instead of connecting to the circle here, you go down like this, and then you circle the interior part here once, and then you go up like this, and then you connect to the point where you started here. And in this way, you get an oriented curve like this. And in addition, the interior here will now be simply connected. So here you can actually use the Cauchy integral formula. So if we call this curve gamma, then you can, for any point z inside here now, you can write that z is equal to 1 over 2 pi I times the integral over gamma of f of w divided by w minus z dw, like this. So this is true for any point in here now. However, this curve is a little bit complicated, and you cannot really derive any nice expansion directly from that. But the idea is now that if we consider the limit situation where these two line segments, so to speak, converge to just one, then you will get 4 different contributions here now. First you get the contribution from this circle, and then the contribution from this circle, and then these 2 contributions here. One's going down and one's going up. But these 2 in the limit will cancel out. So if you call the outer curve here now gamma 1, then you will get a formula like this, that you have first the contribution from gamma 1, 1 over 2 pi I, and then f of w divided by w minus z dz then. But then you also get a contribution from the inner circle here now. And let's call this this inner circle gamma 2. However, you see in this picture the curve will be oriented clockwise, but usually we prefer to have curves oriented in the counterclockwise way. So gamma 2 will be the one with the counterclockwise orientation, and this will then introduce a minus sign here now. So then you get a second term which looks like this. This was gamma 1, and this will be gamma 2, and well, the same integral like this. And the parts from up here will then cancel out. So this will be a formula which is actually true for any z between these 2 circles, including those lying up here then. And now we can try to expand each of these terms, and then it turns out that this will give you an ordinary power series, just as in the case of Taylor expansion or ordinary power series expansion. This one will give you an expansion in terms of 1 over z, an expansion of this kind of type. And so what you will get altogether will be what we call a Laurent series. So let's start by considering the first term here now. And for simplicity now, during these computations, I'll suppose that these 2 circles are centered at the origin here now. So this will make the computation a little bit simpler. Let's start here now with 1 over 2 pi I integral over gamma 1 f of w divided by w minus z dz. And then, just as in the case of ordinary power series expansion, we start here now by extracting. In this case, we extract 1 over w from this expression here now. So we'll get f of w divided by w, and then we'll here have, oh sorry, this should be a dw, and then we get dw divided by 1 minus z over w like this. And here we can now expand this function here, 1 over 1 minus z divided by w, in a power series as usual then. So then we'll get 1 over 2 pi I times the integral over gamma 1 of f of w divided by w, and then we get the sum here now, k goes from 0 to infinity, of z divided by w and to the power k here now. Yeah, and then we can, just as in the case of the power series expansion, we can exchange the order of summation and integration here now, and then we will get the sum k goes from 0 to infinity, and then we'll get here an expression which is 1 over 2 pi I times the integral over gamma 1, and then we'll get f of w, and then divided by first this power w to the power k, and then we have an extra factor w here, so it will be w to the power k plus 1 dw. And then at the end here we can put this factor z to the power k. So now let's turn to the second part here now. We had this expression then. Remember we had a minus sign then, and then the integral over gamma 2 of f of w divided by w minus z dw. Now, in this case, you see that since gamma 2 is the inner curve, in this formula now, the absolute value of z will always be larger than the absolute value of w. So you cannot really do the same trick as last time for the other part, where you extract 1 over w. But instead what we'll do in this case is that we extract from this function the factor minus z here now from the denominator. And then we get a minus sign, which by the way cancels that minus sign out. And so we get 1 over 2 pi I, and then times the integral over gamma 2 of f of w, and then we will have a z down here, and then we will have dw divided by, and then we get 1 over we get w over 1 minus w divided by z, like this. And since now the absolute value of z in this formula is strictly larger than the absolute value of w, this can now be expanded in a convergent power series. So we'll get 1 over 2 pi I, and then we get the integral gamma 2, and then we'll have f of w divided by z, and we get the sum here now, k goes from 0 to infinity, of w divided by z to the power k, so we put the k like that, and then dw. And this can then be rewritten then, again, if we interchange the order of summation and integration, then as the sum k goes from 0 to infinity of 1 over 2 pi I times the integral over gamma 2 of we'll get f of w, and then you see we get times w to the power k. So the w will now be in the numerator, and then dw, and then we'll get this factor z, 1 over z to the power k, and an extra factor from here. So we can write this as z to the power minus k minus 1. So this is the second part then. So if we sum this up now, we'll see that we'll get an expansion of f as first the sum here now, k goes from 0 to infinity of, and then I will write ak times, and now let me just insert this point z naught here now. So I've done the computations at the origin, but now I'll write the general formula if you expand around the point z naught. And then you get this term, so this is the power series part, and then you get another sum here now which corresponds to this one, which will be, well, let's call the coefficients here now first of all, let's note that if we move the index of summation here one step, so we replace k blank k plus 1, then we can write this as a sum. K goes from 1 to infinity of a k minus 1, and then times z minus z naught to the power k. So yeah, so you replace k by k minus 1. And then you get an expression of this form, and then you see that the ak here now, we have different formulas in the case when you use gamma 1 and gamma 2. But with this convention here, when you move the summation index, you see that they will all be given by the same formula here now, whether k is positive or negative. So you will get an integral here now of f of w divided by w minus z naught to the power k plus 1, and then dw. So this will actually be true both for positive and negative k. Actually, when we did this computation, you notice that in the case of the second term, we used the curve gamma 2, and in the first case, the power series part, we used the curve gamma 1. So which one should we write down here if you want a common formula? Well, as it turns out, it doesn't really matter. You see, because remember the region looked like this. Since the function here now will be analytic in this region, the Cauchy integral theorem says that it doesn't really matter if we integrate around the inner curve or the outer curve. So you can here we'll just write gamma, well, or maybe I use small gamma here for any curve which goes once around the inner hole like this. So this could be small gamma then. Yeah, and then let's note that in many situations it can be more convenient to write this expression as an infinite sum which goes from minus infinity to plus infinity in this way of ak. Like this then. So let's now consider some examples of Laurent expansions. So we start with the following function. We consider a simple rational function of the following form then. In this case, you see that you have a function which is analytic in the complex plane, except for 2 points. So at the point -1, you will have a pole, and also at the point 2i, you will have a pole. So what happens now if we try to expand this function around the origin? Well, first of all, you can in this region, you see that the function is analytic inside the unit circle, and there you get an ordinary power series expansion. But you can also consider the annular region between the circle with radius 1 and radius 2, and then you see that the function will be analytic here, and you will get a Laurent expansion in this region which is then different from the power series expansion. And finally, you can also consider the region outside the circle of radius 2 here. And then you get still another Laurent expansion. So let's take a look here now. First observation is that to expound this, it's very convenient to start by splitting this function up into 2 parts then. So it turns out that you can write this as 1 minus 2i times the function z minus 2i, like this, 1 over z minus 2i, and then minus same factor 1 minus 2i times 1 over z, 1 over 1 plus z, like this. So if we start with the region in here, how do we do the expansion? This will then be an ordinary power series expansion. You can, if you take this term here, 1 over z minus 2i, then we just extract this factor 1 over 2i, and we will get 1 over, actually you should extract minus that factor then. And then you get here 1 divided by 1 minus z divided by 2i. And then you see that this is easy to expand now just by the ordinary geometric series. So you get z to the power k divided by 2i to the power k. And this is really the expansion of the first part here, which should insert instead of this function then. And here, instead of 1 over 1 plus z, well, this you can directly expand as some k goes from 0 to infinity of, well, 1 as minus 1 to the power k times z to the power k. So if you insert this expression here and this expression here, you'll get the Laurent's, well, in this case, the power series then for the function in this region here now. But if you go on to this region, the annular region here, then we see that this first part here is still convergent in here. So this this first part will be unchanged in the Laurent expansion in this region here. But this part would diverge, you know, if the absolute value of z is larger than 1. So this has to be replaced by something else. And in this case, what we'll do is actually the same trick as in the proof of the Laurent expansion. We, instead of just, what we do here is that we extract the factor 1 over z first. And then we get 1 divided by 1 plus 1 over z like this. And then you can expand here now by geometric series then, because this will have absolute value less than 1 then. So you get the series, in this case, minus 1 to the power k times 1 over z to the k. And this series then, you see it will be convergent in here. Actually, it will be convergent in the whole complex plane outside the unit circle. So if you now go on to the case, the third case here now, out here, then you see that if we want to Laurent expand the function out there, we can, if we start from this this expression here now, for this term, we can use this expansion. But this will, for this term, we can no longer use this expression because this will be divergent when absolute value of z is larger than 2. So in this case, we have to replace 1 over z minus 2i by something else. And the trick would be the same as here. And we extract the factor 1 over z. And then we get 1 minus 2i divided by z here now. And then you can expand this by geometrical series. And you get some k goes from 0 to infinity of 2i to the power k divided by z to the power k. So this is essentially how you expand this, how you can expand this function in 3 different ways in these 3 different regions.